Welcome back to the deep dive.
Good to be here.
So today we're cracking open something that connects, well, a few different worlds.
Yeah, we're looking at farms, grocery stores.
And maybe even your latest math homework.
That's right. We've got this excerpt, and it's looking at a pretty practical, almost everyday problem.
Which is?
How yogurt spoils, specifically during transport, and what math can tell us about it.
Right. So our mission for this deep dive is really to unpack that. This source suggests using calculus.
Differentiation, to be specific.
Exactly, differentiation, to actually model that spoilage process.
So we're trying to see how a concept like the derivative, something you might be learning, applies to, well, yogurt quality changing with temperature on a truck.
Okay, let's dive in. The source points straight at the derivative.
And if you've encountered calculus, you'll know the derivative. Fundamentally, it measures a rate of change, how fast something's changing.
And this is where it gets really interesting, I think. Spoilage. It isn't like an on-off switch, is it?
Not at all. It's a process. Happens over time. It has a rate.
A rate. And that rate isn't necessarily constant.
Definitely not. And the source really highlights temperature during transport as a key factor. It directly affects how fast that spoilage rate changes. It can speed it up or slow it down.
Okay, so wait. The derivative gives you the rate of spoilage.
Right. How fast it's spoiling at, say, a given moment.
But you're saying that rate itself depends on the temperature.
Precisely. So think of it like this. The rate of spoilage is a function. Depends on time, obviously, but it also depends heavily on temperature.
Ah, okay. So the derivative isn't just giving a single number, it's describing how that spoilage speed changes as the temperature changes.
Exactly. We're moving beyond just saying rate of change to seeing it as a variable rate, influenced by conditions like temperature. That's the core idea the source brings in with differentiation.
So instead of just like a general rule, hotter is faster.
Which we kind of know intuitively, right?
Yeah. Calculus lets you actually build a mathematical model. It lets you quantify how much faster spoilage happens if a temperature goes up, say, 5 degrees.
That's the connection. Using differentiation to create that functional relationship between the temperature and the rate of spoilage. It makes it precise.
And once you have that model, I mean, what can you actually do with it? It sounds interesting, but is it just theory?
No, that's the fascinating part. It's not just theoretical. Knowing that rate, how it changes with temperature, that has real-world implications.
Like what kind of practical questions could you answer?
Well, for example, you could potentially predict the maximum time yogurt could be transported at a specific constant temperature before it spoils too much.
Okay, that makes sense. Or maybe clip it around.
Yeah, you could work out the highest temperature you could allow during transport to make sure the yogurt still has enough shelf life when it arrives.
So it helps find those critical points, like maybe a temperature where spoilage suddenly takes off.
Exactly. Identifying those thresholds where the rate accelerates dramatically. It takes that classroom concept, finding the rate of change of a function, and applies it directly.
The function here being spoilage over time.
With temperature being a major input affecting how that function behaves, its shape, its speed.
It really makes that connection clear, doesn't it, between the sometimes abstract math and a physical process. If you're working through derivative problems, this is kind of the why.
And that really brings us to a key takeaway from the source, I think. These mathematical tools, like the derivative, even if they seem abstract,
they're essential for tackling concrete, real-world issues.
right? They let us move from just observing something to making precise, quantifiable models. Models you can use for prediction, maybe even optimization.
So what does this all mean for you listening?
Well, it means the math you're learning gives you the tools, the framework to understand things that change.
Things that evolve or decay, especially when other factors influence those changes, like temperature affecting our yogurt. It provides a language to describe these dynamic processes.
Definitely. So here's a final thought to leave you with. If a derivative can help model how yogurt spoils,
Yeah.
potentially optimizing how we transport it based on temperature,
What other changing processes are happening around you? Things influenced by variables.
maybe things like, I don't know, chemical reactions depending on concentration, or how quickly information spreads online.
Could the derivative help us understand or even predict those things more deeply too? Something to think about.